Alright, so we're still interpreting geometrically the solution to a system of equations with three variables in it, x, y, and z. So, of course, we talked about what the equation is supposed to look like. Ax plus by plus cz is equal to d, where the a, the b, and the c, and the d, they're just numbers, right? Okay, so a linear system of equations in three variables has three of these. One of the things that we said when we first talked about a linear system is that if you're going to solve that system, however many variables you have, that's how many equations you need to solve it. So if we have three variables, we need three equations, like so. So that's just an example of something that we're going to be able to solve. So you're probably looking at that and your eyes are bugging out going, man, I don't even know. But don't worry, I'll take you through it. It's not going to be that big of a deal. Okay, so remember that each one of these things is a plane, right? Each graph of these equations is a plane. Okay, so and the solution that we're looking for, well, we've talked about solving a system before. It's supposed to be in a point of intersection. Well, the point of intersection for us in three variables, instead of it being x, y, it's going to be an ordered triple x, y, and z that fits into all three of the equations, okay? That satisfies all three equations. So let's take a step back here and remember the vocabulary and how it goes for 2D systems, okay? So for a 2D system, we say it's consistent or inconsistent. It's consistent if you have at least one solution, and if you have exactly one solution that's independent and they just cross at just one point, they intersect at one point, okay? If they intersect everywhere, you have infinitely many solutions. We call that dependent inconsistent. And then finally, the last possibility was that the lines were parallel. They never touched each other. You had no solution. We call that an inconsistent system. All right, so let's look at some of the possibilities then for these graphs of 3D systems, all right? So the first one is over here on the left. This is what it could look like if we're looking for exactly one solution. Remember, that's an ordered triple, x, y, z, okay? And so you just have your three planes that all come together, share one point. So you can kind of look at this as it looks like an x, y, z coordinate grid, but they don't have to meet at right angles. They do not have to meet at right angles, okay? But there's the little point of intersection right there, okay? And that's the only possibility that, that gives us just one solution. Okay, so then we have a couple that might give us infinitely many solutions or no solution at all. So infinitely many solutions, the planes intersect at a line. Well, it could be that they're all the same plane. I mean, that's possible. Or it's possible that where they intersect is a line. It kind of looks like a book that if you kind of fling it open, they all share the spine of the book and all the pages are dangling down. Well, there's just not one solution there. There's infinitely many solutions right there. Okay, so here are some possibilities for no solutions. Well, no solution means that all three of them do not have anything in common. Maybe two of them at a time do, but not all three of them. So in this first picture, any two of them share a line, but all three of them share nothing. Okay. Same thing with this one right here in the middle. The green plane and the red plane, they share a line. Blue plane and red also share a line, but the blue and the green, they don't share anything. There's no solution there because they all have to have something in common. And another case, of course, is if these are all parallel planes, then they're never going to intersect either. Okay, so those are the things that we should expect from our solution whenever we're solving these systems.